Hello and welcome to the support video for this mini set for Fort Hamilton High School on probability questions on the SAT. Here we have 13 questions in the set, but we're going to go over the questions 1 to 10 in this video. Question 1. Two coins are flipped. What is the probability that there is at least one tail? Well, here we can quickly write the sample space for two coins. Each coin has a possibility of two events, heads or tails. And since there are two flips, 2 for the first flip times 2 for the second flip, are 4 total events. Remember that as discussed, to map the sample space, half of the events can start with H of the 4, and the other half will start with T or tails. Then in the next event, you just alternate heads, tails, and you've got the full list of the possible events. Notice that the first row is heads, heads, the second is heads, tails, the third is tails, heads, and the last possible event is both tosses or tails. Since the question was there has to be at least one tail, there are 3 events of the 4, and the correct answer is D, 3/4 or 0.75. Question number 2, what is the probability of rolling a 9 with the pair of dice? Well, again, it takes time to write out all 36 combinations, but if you focus on the idea of the full sample space, dice have 6 different faces for throwing die, and then there are 2 dice, so 6 for the first toss and 6 possibilities for the second are 36 total events. Then focusing on what's possible to sum to 9, the first roll could be a 3 and the second is 6. Also 4, 5, 5, 4, and 6, 3. Those are the only possible events with the sum equal to 9. There are 4 possible events. So we write down that that should say 4 in the numerator and not 9. Sorry, let me fix that for you. So there were 4 out of 36 possible events. Excuse me. Which reduces to 2 out of 18 or 1/9, and the correct answer was C, 1/9. Question number 3. A principal puts the following names into a hat: Harriet, George, Franklin, Edward, Donna, Charles, Betty, and Anne. What is the probability that a female name that ends in a vowel is chosen? Well, here the names look like A, B, C, D, E, F, G, H in reverse. But we know that a vowel ends in A, E, I, O, or U. So it looks like of the female names, Harriet, well, that ends in a T, so that is not chosen. But Donna ends in an A, and Anne ends in an E. We also include Betty because Bet-T, it's just 2 syllables. Bet, the E serves as the vowel for the first syllable, but for T, Ty, Y serves as the vowel in the second syllable. So there are 3 names out of the 8 total, and the correct answer was C. Question 4. The probability of rain in Utopia is 30% every day. What is the probability that it rains in 3 of the 4 consecutive days? Well, it doesn't have to rain every 3 days in a row of the 4 days, because then there'd just be 2 possibilities. But suffice it to say, if it rains, there's a 30% chance, so there's a 70% chance that it doesn't rain. So we start with that binomial probability. Then the possible events are it rains on days 1, 2, and 3, and then it does not rain on day 4. Or it rains on day 1 and 2, does not rain on day 3, but rains on day 4. Or the only day it does not rain is day 2, or the only day that it does not rain is day 1. So I represented that coding as the 4 rows here with R equal a rainy day and N equal a non-rainy day. The probability is by, again, using the multiplication principle, multiplying the probability of each event. So you can see that it's 0.3 times 0.3 times 0.3 times 0.7, which is 1.89%. It's true because the factors are just rearranged. That 0.7 is commuted along the, it should really be moving along the diagonal. So that should be 0.7 for the third, the second, and the first. But I just commuted it to the end because just to show that it's mathematically the same. What I mean is here in this technical note is this is the 0.7 factor. Here it's in the third place, but it still means that those 3 rainy days are 0.3. So I just put it at the end for each of the rows, forgive me. But you can see that those end days, those non-rainy days, have a factor of 0.7. So those are the 4 possible combinations, the only 4 possible combinations. We add those percentages, and we get that 7.56% of the time, it will rain 3 out of the 4 days. Question 5. There are 7 red, 4 green, and 5 blue marbles in a glass jar. If 2 marbles are drawn without replacement, what is the probability that they are both the same color? Well, we have 16 marbles total, and we want to add the probabilities of drawing both red, both green, and both blue as separate independent events. Since we're not drawing with replacement, first we could draw a red marble. There are 7 of those. And then set it aside, and of the 15 marbles left, 6 of them will then be red. That is a probability of 42 out of 240. For them to both be green, well, there are only 4 green marbles. So 4 out of 16 for the first draw. And for the second pick, there's 1 less, and there's 1 less green marble, so 3 out of 15. 4 times 3 is 12 out of 240. And finally, there are 5 blue marbles. So to pick a blue marble first is 5 out of 16. Then there's only 15 marbles in the glass jar, and 4 are now blue. Multiplying together, 5 times 4 is 20 out of 240. By not reducing the fractions, we can add them quickly. 42 plus 12 is 54, plus 20 is 74 out of 240, which reduces to 30.8%, which rounds to D, 31%. So the probability of drawing 2 marbles of the same color is 31% of the time. Question 6. A baseball player has a 60% chance of striking out a batter. What is the probability the pitcher has 3 strikeouts in a row? Well, here we're back to the multiplication principle. At each independent event, there's a 0.6% chance. So 0.6 times 0.6 times 0.6 is 21.6% of the time the baseball pitcher will strike out 3 batters in a row. Question 7. What is the least number of handshakes that are needed for 7 people in the room so that each person has met everyone else? We're talking about the minimum number. Well, here I drew pretending using graph theory, which is a counting tool, that the 7 people are standing together in a room. Person 1 then will walk forward and introduce her or himself to each of the other people in the room. So when person 1 does this, goes around to person 2, 3, 4, 5, 6, and 7, person 1 has done 6 handshakes. Person 1 has now met everybody. We then go to person number 2. Well, person number 2 has already met person number 1, but has to turn and introduce him or herself to the other people. So person number 2 says, okay, I've already met person number 1, but I will go and meet persons 3, 4, 5, 6, and 7 for an additional 5 handshakes. Now person 2 has met everybody in the room. We continue now and carousel around to person 3. Person 3 says, well, I've met persons 1 and 2, and so then goes and meets persons 4, 5, 6, and 7 for an additional 4 handshakes. Continuing with person 4 has already met persons 1, 2, and 3. So person 4 says, well, I haven't met these 3 people for another 3 handshakes. Going on to person 5 is like, well, I've met persons 1, 2, 3, and 4 already. I'll turn and say hello to person 6 and person 7. That's another 2. Person 6 says, I've not met person 7. And then person 7 looks around and says, well, I've already met all these people. They've already approached me with a handshake. So we have to add the handshakes total, and we get the total is 6 plus 5 plus 4 plus 3 plus 2 plus 1, which are 21 handshakes minimum for everyone in the room to meet everyone else. Question 8. There are 10 closed lockers in a hallway. If there are 10 people, each given a t-shirt numbered 1 to 10, the instructions follow. Go only to the lockers that are a multiple of your shirt number, and if it is open, close it. If it is closed, open it. Person 1 goes first and opens every locker. Person 2 goes next and closes every second locker. Person number 3 opens or closes every second number. Shouldn't say that. It should say, yeah, for person 2, opens or closes. Person number 3 opens or closes every third locker. Person number 4 opens or closes every fourth locker, and so on. So after 10 people have gone, how many lockers are now left open? Well, for this problem, we'll make a checking count of the lockers, those inanimate objects, those storage bins that we have at school. So person number 1 walks down the hall and goes to each locker that was closed and opens it. Person number 2 goes down the hall and only visits the even numbered lockers. So that means that person number 2 is closing lockers 2, 4, 6, 8, and 10. Person number 3 goes down the hall. When visits locker 3, will close it, visits locker 6, will open it again, and visits locker 9 and will close it. Person number 4 goes down the hall, goes to locker 4 and reopens it, goes to locker 8 and reopens it. Person number 5 goes down the hall and closes locker 5 and reopens locker 10, and so on. There's person 6, 7, 8, 9, and 10. Well, how do we know if a locker was open or closed? Remember, they all started closed. So with the first visit, they're all open. But then with any time the locker is visited by a person, the person will close or open it, open or close it, depending on its current state. So we need to total the number of times each locker was visited. Since locker number 1 was visited once, it was closed, now it's open. Locker 2 is visited twice, so it's closed again. That's an even number, open then closed. Locker 3 is closed. Locker 4 was visited 3 times, so it's open. Locker 5 is closed. Locker 6 was visited 4 times, so it's closed again. Locker 7 is closed. Locker 8 is closed. Locker 9 was visited an odd number of times, 3 times. So it's open again. So there are 3 open lockers of the 10 lockers in this problem in the hallway. The correct answer was B, 3. If you'd like to review this classic problem, n can go up to a very large number. The solution here is, you can think about this later, is that any perfect square number will have an odd count because you'll be counting like 5 times 5 is 25. So for the 25th locker, for example, it'll be visited by 1 and 25, but the other factor is 5. So since that's a perfect square, there's no rainbow symmetry to it, right? So any perfect square will have an odd count of visits. Let's go to number 9. Number 9 says a meal consists of each of the following. Chicken noodle split pea alphabet soup or salad is choice 1. Then you can choose between corn, string beans, or rice. Then choose between fish, barbecue chicken, or steak, and pick one of the following in the set: cake, ice cream, or tiramisu. How many meals are possible? So you have to decode this as these are 4 different sets. Choice 1 is the soup. Choice 2 is your vegetable. Choice 3 is your main dish meat. And choice 4 is the dessert. So for the first choice, looks like soup or salad, actually. There are 4 items in the set. There are 3 vegetables in the second set, 3 meats in the third set, and 3 desserts in the fourth set. So using the multiplication principle, the total number of combinations of meals is 4 times 3 times 3 times 3, or 12 times 9, which is 108 unique meals are possible. The correct answer was C. And lastly, Meg dresses herself from her dresser with 5 different pairs of socks, 3 different jeans, and 6 different blouses. How many unique outfits does she have? Well, here Megan follows the same law, the multiplication principle. And here we have a set of socks times the set of jeans times the set of blouses. So we have 5 times 3 times 6, which is equal to 15 times 6, or 90 unique outfits. So Meg has 90 different outfits that she can dress herself with. And the correct answer was D. Well, ladies and gentlemen, I hope that this review of SAT probability questions is useful to you in your preparation for your upcoming SAT exam. Thank you, and thank you for watching my video.